So welcome everyone to today's Mathematics 1 class. Let's get started right away. We'll start with a quick warm-up question today. So this is from, where is this from? 2019-2, from the exam 2019-2. It's problem 9, as you can see. And it's about Taylor approximation. So your task is to fill in the sketch corresponding to the information in the problem. I'll give you a few minutes, and then we'll talk about the solution. Oh, you can't see that anymore. Let me see what I can do about that. Apparently nothing. All right, now it seems to work. Let's hope it will stay that way. And once you're done, I'd appreciate a quick feedback on how challenging you found that. As usual, there's a tweetback question on that. All right, just to quickly check in on your progress. Who of you is done by now? Quick show of hands, please. Who wants some more time? It's not very many, maybe one more minute. All right, so here's your vote. And once again, you seem pretty divided on that one. I'd say slightly more on the challenging side than on the easy side. The idea of that problem actually was to have a quick and easy problem about Taylor approximation. So let's take a quick look at how you would solve that. First, what information is available on that function? Well, it's a continuous and 3 times continuous differentiable function, so basically all is good everywhere. And it has a unique local maximum. Let's first look at that information. A unique local maximum at -2, 2. And the second derivative at that point is not 0. So it's either positive or negative. And if it's a local maximum, well, what would that look like? Well, it means the function looks something like this at that point, right? So this is the point -2, 2 here. And that means the curvature needs to look something like this, otherwise it couldn't be a maximum, right? And it can't have constant curvature because the second derivative is not 0. So that what the function locally looks like here. That means for the Taylor polynomials, well, we're interested in the first order and the second order Taylor polynomial. First order is obviously a line, so that would look something like this. Because we have a maximum, so that means the first derivative must be 0 as the second is not 0. Okay, so this is t1 f of x at the point -2. T2, well, this is basically T2. Needs to be a parabola with the same curvature at that point. So this is T2 f of x at -2. And then let's do the same thing for this other part of information that we have. We have a unique local minimum at 2 -2. So this is this point here. Unique local minimum, so things are pretty much reversed there. Second order Taylor approximation should look something like this. So this would be T2f x at 2. And the first order Taylor approximation should look like this. T1f x at 2. Right, so what will the function look like? Well, now you have that information. Basically, it will approximately look like that green thing here and here. And it's continuous and differentiable in between. So something like this, I'd say. Well, it's not very good. Something like this here. And then let's go on. Make it approximate this. Something like this should look like a good first guess, right? So that could be what that function might be. We don't know anything about limits, right? So if you draw something like that, would also be a valid guess, as long as you don't get any more local minima or maxima. Right? We don't know anything about, we know those are unique, so there's no more local maximum, there's no more local minimum, just these two. So please don't make it bend anymore, but something like that is fine, or something like that is also good. Whatever you do here is fine, right? We don't have any information on how it behaves in the limit. Okay, so pretty much that was my expectation here. Any questions on that? Yes. Sorry, if it's? So that orange one, like if you didn't do that, but instead something like this? No, that would be wrong, because you know this is a maximum, right? And that means the first derivative must be equal to 0. Okay, so the slope of this line is 0. It needs to be perfectly flat. All right, question? Sorry? The 8 credit, I don't really remember, but I think probably maybe 2 for F. And then we're left with 6, so I guess, just a quick guess, I don't remember. I'd say something like 2 points for F, maybe 3 points for those two, and 3 points for those two. Yeah, I don't remember if I did that 2-1 or 1/2, something like that. So the information that's 3 times continuously different, why is that important? Basically just because I need to know that all those derivatives actually exist and are continuous. Yeah, I just wanted to make sure that nothing bad can happen. Yeah. How do we come up with this one? Oops. With this one, for example? Well, the idea here is, you know it needs to be a parabola, right? The second order derivative tells us something about the curvature of the function. So it needs to bend in the same way as the original function. Okay? Now we do know that this is a local maximum in this case. So that means the function needs to first increase and then decrease. Now for the second order Taylor polynomial, we need a parabola with the same kind of behavior. It needs to first increase and then decrease. So basically the only choice is a parabola that looks like this. Does that help? Oh, good. Any more questions? Let's take a quick look at the tweet back here. Is the apex of the green line at the local minimum maximum? Yes. So the apex of that parabola is at the local minimum and maximum. It has the same minimum and maximum here. Still get points if I label the functions. Would I still get points if I labeled the functions the wrong way? You might get points, but of course I'd have to take away some of those points if you put the wrong labels there. I don't really know. Is there a problem with the camera? I hope not. So for those following us on the live stream, the camera seems to be working. If it doesn't for you, then please leave a comment and I'll see what I can do. All right. So let's go on with more exciting facts about Taylor approximation. You remember, hopefully, we've talked about Taylor polynomials and Taylor series in the previous classes, and just as a reminder, this is the formula for the Taylor polynomial of order n. So basically it consists of taking derivatives, evaluating those at the point where we evaluate the Taylor polynomial, and then summing up terms like this. Yeah, so kth order derivative over k factorial times x minus x star to the power of k, and you sum up from 0 to n. We also defined the remainder. So for any x, the remainder is defined as the function value minus the function value of the Taylor approximation. So basically that's the approximation error that we would make if we replace f by its approximation at that point x. Of course, that depends on the point. If x equals x star, then both have the same function value by definition. So of course the remainder would be 0 there. But as we move away from x star, we expect the remainder to be hopefully still small as we're close to x star, but it will probably be increasing as we move away from x star. And now, of course, an important question is there a way to control that remainder? Or in other words, what degree do we have to choose if you want to guarantee a certain error? One question that I think has been on the tweet back before is why do we care about Taylor approximation? Why do we need that? And one very important use case for Taylor approximation is, for example, if we want to numerically approximate solutions of differential equations or differential equation systems. Now, many important processes in technology can be modeled through a system of differential equations, and we talk more about that in the next semester. For example, if you want to compute, if you want to launch a rocket to the moon and you want to compute the path that it takes, I want to make sure it actually hits the moon at some point, then you would model that through a complicated system of differential equations. Usually, it's hard to come up with an explicit solution for these systems, or it might not even, usually it's not possible to do that. So what you have to do is you have to approximate those solutions through numerical approaches. And one important aspect in doing that is approximating the function that you are looking for through a Taylor approximation. And you refine that Taylor approximation. You move from point to point to get function values of the function that you're looking for. And at each of those points, you compute a Taylor approximation in the hope that this is a good approximation to the actual solution you don't know, at least locally around that point, and then you infer how to move on from that point, right? So if you have, for example, this rocket launch path to model, you'd start somewhere, you try to compute, you try to infer information about the Taylor approximation from the differential equation system, because that tells you something about the behavior of the derivatives, so you know something about those from knowing this point and the function value at that point. And of course, you would have some starting, I mean, you know where you start, right? So at that point, you know exactly where your path is. And then the system tells you something about how the rocket would move in the first few meters, right? So you know it would move straight up, for example. You take that approximation, you move your rocket a little bit to that point here, and now you say, well, I know that is a point on my path, or at least very close to a point on my path. Let's do the same thing again. Approximate at that point, get some information on my path, and maybe now that bends a little, right? So the next point on my path is this, and then I get here, and then I get here, and then I get here, and then I know that my algorithm for steering that rocket is going in the wrong direction. So I'd have to work on that some more. Okay, so that's one very important use case for Taylor approximation, numerical approximations of complex technological systems, to put it very general way. And of course, what you need to be able to do is you need to control the error that you make, right? I mean, if you just want to hit the moon somehow, a few kilometers don't really make a difference. But you can't afford to miss by a very large amount. On the other hand, if you want to land your rocket on a very specific spot on the moon, it might be more important to control the error. It might, a few 100 meters might make a huge difference there. So usually you have an idea about the error you want to allow for your computations. And that means you need to know what degree of Taylor approximation you need to get the error right. Obviously, you don't want to have that degree too high because it will complicate things a lot. or it might mean you can't even do the computations anymore, but you want to have the degree high enough so that the error is small enough. And that's why looking at this remainder, this approximation error, is important. So that's what we are doing in this section on Taylor approximation. All right, basically what we want to know is, how does this error behave if we are close enough to that point x star? So in practice, you have two things you can control. First, the degree of Taylor approximation. And as I said, you can't make that too large because otherwise you can't use it for computations anymore. And of course, you can control your step size, meaning how far away do I move from my current x star? Yeah, so you can control an interval around x star where the approximation is good enough. So you want the degree low, but of course you want the step size large so you don't have to do too many steps in your computation. Yeah, so those kind of work against each other. And that means what you would like, of course, is that your error is small. And specifically, you want the error to be close to 0 as x moves towards x star. And preferably, you want something like this here to happen, right? That means the error of approximation approaches 0 as x approaches x star. And this here is going faster than this. Right? So basically this is a movement linear speed. Right? X moves towards x star linearly. And that means the error needs to decrease faster than linearly if you want to make sure that this limit is approaching 0. So let's skip over that computation here. Right? In other words, what we want is this error should be something like a function that looks like this, where this second part here has a limit of 0. Right? You don't want that to go to infinity and then maybe outweigh this. Instead, you want it to go to 0 in the same direction as this here. And now here's a theorem that tells us that usually things work as they should. So if you have a function that is continuously differentiable often enough, n times if you want to go for degree n, in some open interval, and we have a point in that interval, then there exists such a function that has a limit of 0 such that the error can be written in this way. Right? So it kind of behaves nicely. But of course, that doesn't tell us anything about explicit bounds. So we still don't know how large the error will get for any given point in the interval. And that's where the second theorem comes in. That's what we mostly use in these approximation computations. So again, set up as usual, we have an open interval, we have a point in that open interval, a function that is differentiable with sufficiently high degree. This time we need n plus 1 if we want to go for degree n. And then we have the following fact. For every point that we use to develop the Taylor approximation, there is a point between x star and x, the point that we are evaluating at, with the following property. Maybe let's look at that point here. So the remainder, if you look at the difference of the function value at x and the value of our approximation at x, the remainder can be expressed in this way. And basically that is almost the same thing as the n plus first term of our Taylor polynomial. Only difference is we're not using x star here, but instead we're using this point x tilde. And all we know about x tilde is it is contained somewhere in this interval, right? So here we have our x star, right? This interval is somewhere around x star. We are interested in evaluating the function, say, here at x, and then all we know where there is some x tilde somewhere between those two. We don't know exactly where that is, and the theorem doesn't tell us, and usually there's no way of computing that. but we know bounds, upper and lower bounds. And often we can use that to bound this error here. And I'll show you an example in a minute. Okay, so this is an not quite, but somewhat explicit way of computing that remainder. And that is what we use to control the error that we make. All right, let's take a look at an example. So here's an example for the exponential function. You remember that we've talked about the Taylor polynomial for the e function around 0. Looks like this. And what we'd like to know is whether evaluating that Taylor polynomial for a sufficiently high degree is a good approximation for the e function anywhere. Of course, we know it will work at 0, but maybe it would be great if it even works if you move far away from 0, right? Just by taking a high enough degree. So in other words, the question is, if we increase the degree, if we let that go to infinity, does that thing converge to the e function at all points x? And that's what we're looking at here. And well, another formulation of does that converge to the e function is looking at the remainder. We know the remainder looks like this. And then the question is, does that remainder go to 0 if we increase the n? Will that be small? And if it is, then we know our Taylor series is actually equal to the e function. I've told you that this works already, but here's the proof that it does. With this remainder here, we do know the nth, or the n plus first derivative of the e function. It's just the function itself, so it's easy to express that. The rest is very straightforward. So we need to compute the limit of that as n goes to infinity. And all we know is this x tilde is somewhere between x and 0, whatever this x is. So preferably, this will hold for every possible choice of x. But maybe if we don't get that, then it would also be fine to prove that for some interval around 0, right? So maybe we only get that for x's that are smaller than 1 or something. That would be a good start, at least. Yeah, so we know where we can rely on our approximation. The proof for that is somewhat technical, so I'll not go into the details for that. If you're interested in that, take a look at the video. Yeah. Well, why this is constant? Right, so the point is we're taking the limit, maybe like that in front of you. We're interested in taking the limit of that for n to infinity, right? We have chosen a constant x star, that's 0 in this example. We have a constant x. We're interested in some value of x, but whatever value we choose, in the beginning is constant from now on. And preferably, we'd like our proof to work for all possible choices of x, but if we can't get that, then we restrict that suitably, right? And then we know there is this x tilde somewhere in the interval between 0 and x, and that also doesn't change. Right? We know that exists by that theorem, and it's constant. So if you split off that part, right, with the n0 and this x tilde and this x, all of that is constant. The only thing that changes is the n. And in that proof, what we did is we replaced n by the expression n0 plus t. So what changes is the t part, right? We start at n0 and then we increase by increasing t. So what does change is this and, of course, this. So the question basically is, will this here go to infinity faster than this? Who will win, right? And if we're lucky, this part here will converge to 0. This part here will converge to 0. And of course, that means this constant doesn't matter. Yeah, so that's why this is a constant. Does that explain things? Good. So as I said, this is somewhat technical, and I wouldn't expect you to be able to reproduce that, but I hope you understand at least the general idea behind that proof. What I need you to remember basically is the outcome. And that is, well, two things. First, what we can show here is that this actually converges to 0 no matter what x we choose. Right? And that means this here, this Taylor series, actually is equal to the E function. It's not just a Taylor series what we don't know anything about. What we know it converges, and we know it converges to the E function. So that does the right thing everywhere, no matter what x we choose. Okay, so I need you to know this Euler series. And of course, what we have shown in a way is that terms of this type here, so the summons of this series, x over k, x to the power of k over k factorial, these terms converge to 0 if k increases. Right? We did basically show that, but we could also say once I know that this series converges, well, I know the summons have to converge to 0, otherwise the series couldn't be convergent. Yeah? And this is a fact that we use sometimes. A sequence of the form x to the k over k factorial converges to 0 as k tends to infinity, no matter what x we choose. Okay, so this was kind of the easy example. A few technicalities, but at least the outcome was nice. The next example is not that nice. So here we're taking the logarithm as the function that we want to approximate. What we actually want to do is, so you remember the logarithm basically looks like this here. Yeah, so this is the log function with log of 1 being 0. So this is the point 1. So unfortunately, 0 is not a very good point to develop the Taylor series because the function is not even defined there, right? We can't do that. On the other hand, having 0 in there is a really nice choice for the Taylor series. It looks a lot better if we have 0 and not something like x minus 7 to the power of whatever. That makes things a lot harder. So what we do is we apply a little trick. And instead of considering the function ln x directly, we consider the function ln x plus 1. So what we do is we move that whole setup a little to the left. So basically what we have here is function that, yeah, maybe that is not very good. That looks like this. Yeah, so this basically is the function ln x plus 1. And the only reason we do this is we want to develop our Taylor series around 0, and that function is defined and nice at 0, and not at 1. So basically we just move that 1 to 0. That's all we do here. Okay? So that's our function f, and then we can set x star to 0. Basically just a technicality to make the result look nicer. All right, and then what we have to do is we have to compute derivatives, and of course you know how to take derivatives of the log function, so that's what we do here. And that gives us an idea of how the general derivative looks like, and this is what we arrive at. So it's a formula for the kth order derivative of that ln x plus 1 function. Now if you evaluate that at 0, which we need for the Taylor polynomials, here's the result. Well, that looks pretty nice. So it's easy to write down the nth Taylor polynomial of f around 0, and that looks like this. And now, of course, the question is again, does that thing converge? And if so, does it converge to the original function? Or will it converge to something else? So again, we need to look at the remainder. And for the remainder, remember we need that formula here. that x tilde is usually not the point x star, so it's not 0 here. That means we need the general formula for the remainder, right? Not this one, but instead this one here. Luckily we have that, so what we do here is we just use that, right? Substitute that formula here. Then do a little reformulation. Basically just cancel out that and put those in here. So we get that. And for the error, we usually, of course, we're usually not interested in the sign. Yeah, we're not interested in whether that function is, if the approximation is above or below the original function. We just want to know how far away it is. So that's why we usually operate with the absolute value here. And of course, that has the advantage of doing away with that sign change. So we can just forget about that. Okay, so in this case, this is the formula for the error that we get. And unfortunately, the analysis is not as pleasant as it was before. So now we have to distinguish a couple of cases. The first case that we look at is x is between 0 and 1. And in this case, we find all is good, right? What we can do now is we can simply bound x by 1 from above. Right, so we have, let me maybe draw this. Here's 0. Here's 1. Our x is somewhere in there. And we know our x tilde is somewhere in that interval between 0 and x, right? So what we know is x is less than 1 or less or equal to 1. So we can just bound that from above. And we also know x tilde is at least 0. So we can bound that from below. And as this is in the denominator, that means we get a bound from above for the whole expression. 1 over x tilde is then bound from above by this. And luckily we have this plus 1 in here. Yeah, so we don't get a 0 in the denominator. That would not be a useful bound, but with the plus 1, it works. So what we get in the end is a bound that looks like this, 1 over n plus 1, and of course that goes to 0 as n increases. So the remainder goes to 0 as the degree increases, and that means on this interval, all is nice, and our Taylor series will actually be equal to the ln x plus 1 function. However, an important part in this thing was bounding this x, right? So if we didn't have 1, but instead something like x to the power of n plus 1 for an x that is greater than 1, then things might not look as good anymore. And well, if you actually look at that case here, so x is now greater than 1, we get an expression like that for the summons of the Taylor polynomial, right? For these things here. So in the absolute value, this is x to the power of k over k. And for k greater than 1, we know this does not converge to 1. Not converge to 0, sorry. So of course that means this whole sum will not converge, and thus the Taylor series on that interval doesn't even converge, let alone converge to the function that we started with, right? So in this case, we get this useful approximation only for the interval from 0 to 1. And just as a remark, one can also show this holds for the interval between -1 and 0, 2. So we have this symmetric situation. For an interval of length 1 around the point 0, we get a good approximation. That is actually useful. For anything beyond that, so any x greater than 1, the approximation doesn't work anymore, not even remotely. It doesn't even converge. So we can't use that. Okay, so that's an example where the Taylor series does not even converge, let alone converge to the function we want. So generally, you'd have to be aware of those limits in a way. If you want to use Taylor approximation, always make sure that your function actually converges, or in other words, that the interval is small enough so that you can be sure the function converges as you increase the degree. Otherwise, your rocket launch will fail. And there have been examples of that in the past, where people made exactly that mistake. All right, so that's enough theory about Taylor approximation. Maybe let's take a look at some practical examples, actually. Let's get started with an example. I think we did example 1 yesterday, so let's do example 2 today. So here's the problem statement. Consider the function f defined on the real line with codomain R, given by f of x is 2 to the power of minus x. And your tasks are the following. First, determine the Taylor series of that function. So the Taylor series of f around x star equals 0. So tf x 0. Let's start with that, and then we take a look at where this series actually converges and what it converges to. Just a quick show of hands. Who of you is done already? Who wants some more time for the first part? So maybe let's give it a few more minutes. For those that are already done, feel free to think about a second question, which is, for which values of x does this series converge? So let me ask once again, how are you doing? Who is done already? Who wants some more time? All right, not that many. So maybe let's discuss the solution for A so that you can then work on B with the correct Taylor series. Give me a second. So we want that function 2 to the power of minus x. And usually if I have an exponential function where the base is not e, my first approach is to reformulate it in a way such that the base is e. And you know how to do that, hopefully. This is e to the ln of 2 to the minus x. And you can easily reformulate that as e to the minus x ln 2. And now I hopefully know how to take derivatives of that function. So what we need for the Taylor series is an idea of what the derivatives are going to look like, specifically at the point 0. So let's start with the function itself, the 0th derivative, and then 2. And then f at 0 is e to the 0, and that's 1. The first order derivative is going to be, well, that same function, e to the minus x ln 2. And then chain rule, I need to multiply that by the derivative of, of the argument. So that part here. Well, that's a constant. The minus is also a constant, so the derivative of that is minus ln 2, right? So times minus ln 2. Or in other words, let me just rewrite that slightly so that it looks a little nicer. Minus ln 2 e to the power of x ln 2. And then the function value at 0 of that expression is, well, if I substitute 0 here, the result is e to the power of 0, so still 1. And now I have this minus ln 2, so it's just minus ln 2. If I continue that process, you hopefully see where that is going. This is a constant, so I don't have to worry about that. I did compute the derivative of that part already, so that just means this reproduces, and I'll get another minus ln 2. So this is my original minus ln 2 times the new minus ln 2 that I get from taking one more derivative times minus e to the minus x ln 2. Or in other words, that's minus ln 2 squared e to the minus x ln 2. And again, at 0, this e part will be e to the power of 0, so 1. So what I get is minus ln 2 squared. And in case you're wondering why I don't do away with that minus, because minus 1 times minus 1 is obviously plus 1, I just want to keep it to see the pattern better. Right, so that continues in that same way, and that means the third order derivative will then be minus ln 2 to the power of 3 e to the power of minus x ln 2. And if I evaluate that at 0, what I get is minus ln 2 to the power of 3. And so on. So generally the kth order derivative, or maybe it's an n because one is series anyway, n of x is equal to minus ln 2 to the power of n e to the minus x ln 2. And if I evaluate that at 0, what I get is minus ln 2 to the power of n. So I can now write down my Taylor series, Tf of x around 0 is, remember, that is the nth derivative of f at 0 divided by n factorial times x minus x star, that's 0 here, to the power of n from 0 to infinity. So here I get n from 0 to infinity minus ln2 to the power of n over n factorial times x to the power of n. So that hopefully is the Taylor series that you got. Just as a very quick feedback, who of you got that result? All right, that seems good. Now the next question is, for which values does the Taylor series converge? And basically there are two ways to approach that question. One would be what we've just seen. Take a look at the remainder, use that remainder formula, and then try to prove that converges to 0. However, that question leaves a little more leeway here. It doesn't ask us to show that the Taylor series converges to the function that we started with. We would prove that if we look at the remainder, and that's going to be part C, by the way. But for part B, if this is the only question that we have, there might be an easier solution. And that is, take a look at that series here, and then see if you can use some convergence criterion that you know to prove that this converges, or to see for which values of x you can prove convergence. Right? So for example, ratio test, root test, things like that might also work here, and are usually far easier than dealing with that remainder. So in this case, I'd say try one of those tests, one that seems suitable for that situation, to see if that is sufficient to see where that converges. Quick show of hands once again. Who's done already? Who wants some more time? Maybe I'll give you 2 or 3 more minutes. That should be sufficient. And for those that are done, of course, the next and last question will be, does the series actually converge to the function? So feel free to start thinking about that one. All right, so let's take a look at that part so that we have enough time to discuss the last question as well. Now remember, this here is the Taylor series that we've come up with in part A, and we want to know for which values of x that converges. I already said we can employ root or ratio test. Now basically what you do is you say, well, this is a series, and these here are the individual summands of the series. And please note this includes the x to the power of n, right? This is what you sum up over. And I just try to apply a test that tells you whether that converges or diverges. And of course, the result might depend on the value of x. And that will hopefully tell you, or at least give you a hint, of what values of x are appropriate for converging and which might lead to divergent series. Of course, it might also end with an inconclusive test. In that case, you'd have to resort to more powerful materials, more powerful theorems. But it's usually easy to try that. So I'd give that a try first, see if it works, and then you're done with that. All right? So in this case, I'd say the ratio test would be a good first try. Remember, the ratio test is asking you to evaluate an plus 1 over an in absolute value. So if we use that, our an plus 1 is minus ln2 to the power of n plus 1 times x to the power of n plus 1 over n plus 1 factorial. And I better move that a little. And then I divide by an, or I multiply by 1 over an. 1 over an is n factorial over minus ln2 to the power of n times xn. Right? So this here is an plus 1. This is 1 over an. And I have absolute values here, so I don't have to take care of the signs. And now a lot just cancels out, right? I have this minus ln2 to the power of n plus 1, and here I have to the power of n. So I'm left with 1 minus ln2, and I'm taking the absolute value, so I don't care about the sign. Just forget about that. Then for the x's, n plus 1 and n here, so I'm left with just 1x, or the absolute value of that. And then I have n factorial here, n plus 1 factorial here, so this is an n plus 1. And I'm asking, what is the limit of that as n approaches infinity? Well, there is no n in here, only n left is here. So for every constant value of x, no matter what that is, this will always go to 0. And this works for all x in R. So remember, the ratio test tells us, well, if that expression has a limit that is strictly less than 0, then the series is absolutely convergent. So that's the outcome here. And that means the Taylor series converges even absolutely for all x in R. And again, one possible outcome might be that this limit is not just a fixed number, but it might depend on the value of x. And then you get some equation for x that says, well, this expression must be less than 1 so that you can be sure this thing converges. So you'd have a condition on x, and that will tell you what interval you have for the x's, right? In this case, it's not problematic. This thing converges everywhere. Okay, questions about that? And let's tackle the last part, and that is, we now know that this Taylor series converges. We don't know what it converges to. So the last natural question is, for which values does the series converge to the function that we started with, if at all? For which values of x in R does TF x0 converge to the original function value? And to get you started, in this case, we will need to take a look at the remainder and remember this remainder formula that we had. So for a given x value, we are looking at this expression here, the n plus first derivative at some x tilde times x to the power of n plus 1 divided by n plus 1 factorial. And of course, feel free to take the absolute value of that. And in case you forgot, we evaluated this expression here already. In the beginning, we computed the derivatives. So that will be minus ln2 to the power of n plus 1 times e to the minus x tilde ln2. That's the expression for this derivative. I'll just copy the rest. So the question is, can you show that this arrow converges to 0 for at least a few selected values of x? need a couple of minutes to write down the solution, so let's check quickly. Who of you has done already? 1, 2, 2.5. All right, maybe let me briefly show how to do this. It's not that hard if you have some experience with those kind of things. We have the absolute value here, right? So first thing we can do is, of course, we can completely forget about the signs. We're not interested in those. The hardest part is probably getting this thing here bounded in a useful way, right? What we do here is, what we can do here is, can say, well, this is less or equal to, let's first forget about those signs. So let's just take ln2. ln2 is non-negative, so we can just take it as it is, to the power of n plus 1. Over n plus 1 factorial, we just copy that part. And for the x to the power of n plus 1 part, again, we can just copy that. And we can also take the absolute value here, right? That's an upper bound. Now, what we still have to take care of is this expression here. We need to upper bound that as well. What we do know is this x tilde here. Remember, that is somewhere between the point 0 that we used for computing the Taylor polynomial and the point x that we are currently interested in. So it's some general x, right? That might be on the right, and then x tilde might be somewhere here. Or we might also have an x that is on the left of 0. And then x tilde would be somewhere here. Okay, in any case, we have this e to the minus x tilde times some constant function. The e function basically looks like this here. You hopefully remember that. Yeah, so it's increasing monotonically. And that means to get a bound, we just have to find a value to the right, basically, of that interval. So in this situation here, we can just bound that by e to the power of x. In this situation here, e to the power of x is actually smaller. So the right bound would be, or one possible bound would be just flip this around and take the absolute value of x for the bound. Okay, so one possible way of bounding that is, well, saying this is bound by e to the power of the absolute value of x, and we just copy the ln2. Doesn't have to be a great bound, just one that we can control. Right, and then we're basically done with it. This e to the power of x ln2, that doesn't depend on n, so we can consider that a constant. Then we have x ln2, absolute value to the power of n plus 1. We can just put those here together. And we have n plus 1 factorial. And you'll remember somewhere near the beginning of the lesson, we talked about expressions of that type. X to the power of k over k factorial. And I said that what you need to remember is that this is a sequence that tends to 0 as n tends to infinity. And here's where we need that. Right? So if n tends to infinity, this second part here tends to 0, and that's a constant. Depending on x, of course, yeah, but for any fixed x, that is a constant. So it doesn't really matter. If we move n high enough, this tends to 0, so this whole expression tends to 0. So this whole thing goes to 0 as n goes to infinity, and that means if we just tune our degree high enough, we'll always get an approximation that is good enough for that function. So actually what happens is the Taylor series of f around 0 is equal to f of x. So it does converge, and it even converges to the function that we want. And remember, that is a difference, right? Even if we know the Taylor series converges, it might converge to something totally unrelated. Unless we can prove that this remainder here goes to 0, as we just did, we don't know whether this approximation actually approximates the right function. That is, of course, the hope, the intention, but it doesn't have to work, unfortunately. Question, yeah? Doesn't ln2 to the power of n plus 1 also diverge? So this part here, yes, but divided by n plus 1 factorial, it still works out. Yeah, so it doesn't really matter whether I have x. I mean, x is constant, right? This here is also constant. So some constant to the n plus 1 over n plus 1 factorial, that always goes to 0. Okay? That was what was shown before with this technical approach, if you remember that. All right, so that's it for today. That's all about Taylor series and approximation. If you have any more questions, of course, I'll be happy to answer those in exercise class. And otherwise, I'll see you on Monday for integration.